You'll be continuing with exponentials in grade 12. So we wanted to make sure that you had some exposure to applications using the exponential functions. So I'm just introducing you to the most general form of the equation that you'll see, as well as some common contexts that use exponential growth. Now, in reality, most things are not directly exponential. Often they involve a combination of functions, but some of these are directly exponential, and I will try to let you know which ones are true. So the two most common exponential growths you'll see are population growth, like bacteria. So this will only be true in like a culture context. So if you had, like in a science lab, you were growing a culture of bacteria, then it would follow this kind of exponential growth pattern. And compound interest always does follow this. Now, whether or not it's valid for all values of t actually does depend on the actual type of growth that it has. So it does get a bit more complicated. But in general, the formula you're seeing here is what we're going to look at. And that formula, what it's telling you is that some population or value, whatever you want to think of it as, can be found by looking at the initial value multiplied by 1 plus the rate. So rate's usually given to you in percentage, and then you convert it to a decimal. So this is, increase, hence the fact that you're growing. So you're going to be going larger because the value will be greater than 1. And then that's put to the exponent t, which would be usually be time in both of these contexts. Then you get exponential decay as an option as well. So here's one where they're not always directly. This one is, though. Again, this would usually be this has been tested for sure in lab situations, but it's looked at as being true in real life situations as well. Depreciation, so this would refer to like how the value of your car goes down as time goes on. That idea of like the moment you drive your car off the lot, it's decreasing in value. And also the concentration of medication in the human body. That's one where it's really is a combination of functions. It's not directly exponential, but for the purposes here, we'll start using it as that. And by the end of grade 12, you might actually develop a slightly more accurate one for this. And that equation you can see is very similar. You've got your initial amount here again. The biggest difference here is that it's 1 subtract the rate, because this time we're decaying. So we're going to end up with our base value being between 0 and 1. So you end up with a decreasing function. So decrease versus increase for exponential growth. And these are two somewhat particular versions of what I was showing you on the first screen. So when we are talking about exponential growth, 1 plus r, what if your rate is actually increasing by 100%? So that's what we call doubling. So if something is doubling, then your r is 100%, which of course is, 1.0 when you turn it into a decimal. So when you look at 1 plus r, you get 1 plus 1, which is 2. So hence you're seeing the 2 in here for the 1 plus r. And then same for half-life. So it's decreasing by half, which would be 50%. So you get 1 minus r, 1 minus 50%. 50% is 0.5. So that's 0.5. So that's where you get that half from. And then you'll see the other big difference here is in the exponent. You're getting this t over h. So h is your half or doubling time. So if it takes, let's say your work is in hours, and it takes you, and it takes the population let's not use the number 2. Let's say it takes the population 5 hours to double. So if you're told something like that in the question, then you know, oh, I'm looking at the doubling example because that's when my rate is 1. And so that 5 ends up being part of that exponent. So whatever your initial population was, doubles every 5 hours. So time in hours divided by 5. And so how that functions there, so like that t over 5, so that means every 5 hours you're going to have the exponent, have the base be multiplied once. So you'll see like when you have t being 1, then, when you have t being 5, then you get 5 over 5, which is 1. So that's 1 doubling period. So you'll be p naught times 2. Then when you get up to 10 hours, 10 over 5 is 2. So you're doing 2 squared times p naught. So you're seeing there you doubled again. So every 5 hours it doubles. And so what you're going to do now is try the problems in the Jamboard in the groups that are assigned using the breakout rooms. And please refer to the instructions for timing of everything.